Hello everyone. Here in this video, we are solving a problem from simple harmonic motion. Let me read out what's the problem is. One end of a long metallic wire of length L is tied to a ceiling, right? So I will take that part of the problem and try to draw the diagram for you. So there is a ceiling to that a long metallic wire of length L is attached. The other end is tied, so that's the other end of this, the other end of the part is the other end is tied to a spring constant K whose mass is negligible. So I shall draw a spring here of spring constant K. Then a mass M hangs freely from the free end of the spring. So I can continue this further. Here a mass M is attached at the free end. The area of cross section and Young's modulus of wire are A and Y. So this Young's modulus is having a area, this wire is having area of cross section A, Young's modulus is Y. When mass is slightly pulled down, that means here it was pulled down this way and released, it oscillates. So there is a restoring force, that's why it is going back. So it oscillates with a certain time period. I need to calculate what is the time period is. So you can clearly see there are two parts of the problem. One is wire, another one is spring. Now, this wire is also behaving like a spring because when you pull it down, it is going back and oscillating. So, what is the spring constant of that wire? Approximate force constant of that wire I want to calculate. You know, I can write a formula that that wire experiences stress called longitudinal stress. That is stress along the length of the wire. It is defined as the force acting along the length per area of cross section. Respect to this longitudinal stress, there will be a strain. That strain is called longitudinal strain, which is defined as increasing the length of the wire. This wire will increase its length by a small value delta L by original length L. You know, as per the basic definition of elasticity, as per the Hooke's law, longitudinal stress is directly proportional to longitudinal strain. Proportionality can be eliminated with a constant modulus of elasticity. Here, modulus of elasticity is called Young's modulus, Y. So, Y here means Young's modulus that is given for you in the problem. This implies force can be written as YA by L and delta L. So, this equation, what I am writing is something uh, similar to F equal to K into delta X. F is say delta X, delta L are same. So in the place of spring constant, we have something. In place of force constant. That implies we can say force constant of the wire K can be written like YA by L. We have spring constant of spring as K itself. So if you observe it carefully, this is one part, right? And this is another part. The upper part has some spring constant this much. The lower part is having some spring constant this much. And you are slowly disturbing like this, slightly disturbing like this. So it's very clear if you observe a little carefully, it is very clear that wire and spring are in series. You know, the effective spring constant of the two springs in series 1 by K series is 1 by K1 plus 1 by K2. Our K series is K1 K2 by K1 plus K. Here K1 is this much, Ya by L. K2 is K itself. So what happens to our K series then? K1 K2, that is Ya by L and K divided by K1 plus K2. Ya by L plus K. So if you simplify this further, it will become YAK by L in the numerator. The denominator of the denominator, L is the LCM, YA plus KL. So this denominator and this denominator will get cancelled. So what is remaining is YAK by YA plus KL. That is the effective spring constant of the entire system itself. Once if you know the effective spring constant of the system, it's very easy to find out the time period of that oscillatory motion. Now the formula for the time period is 2 pi into root of m by k effective or k series. We know the k series already. 2 pi by t equal to 2 pi into root of m by k series is this much. YAK by YA plus KL all under square root. So if you rearrange the terms, 2 pi into root of n, denominator of the denominator comes to the numerator, YA plus KL divided by YAK. That is how we can find out the um, time period of this system basing on the concept of simple harmonic motion, right? That's it. Thank you for watching. We'll continue further in the further videos.